Hi everyone. My name's Matt Whittaker. I work here at the university at Prince City and in John Dalton, which is our science and engineering building just across the road. I'm the technical specialist for polymers and additive manufacturing, and very recently robotic large-scale additive manufacturing. So a couple of terrible photos of me, teaching some students about injection molding and making some filament out of seaweed, which these came in Oxford last year, so we see in the seaweed stuff we do. I mainly focus on bespoke materials. So we have a really strong electrochemistry research group led by Professor Banks at MMU, and a lot of our research is focused on making bespoke filaments to detect things. So we make custom filaments for detecting heavy metals in drinking water, for example. I want to start today kind of a dirty secret with 3D printing. Anyone here who's got a box at home that looks like this one on the left? Because I know I do. A lot of us collect all of this waste, and we think we keep it. We think, oh, at some point we'll be able to do something with this. Has anyone actually done it yet? It's much harder than it comes across. On the left is the box of shame from our lab group. So this is a box that I stick with all over it. So PLA only. That was my collection method. In the middle, this is Print City, which is about a mile that way, which is our university's 3D print hub. We have a lot more 3D prints going on there. So we have a separate box for each different color of PLA, and then we have a couple of different ones for ABS, PETG. And so for this bit of research, I just concentrated on the white PLA. So that bag on the right was, I believe, about 3 months worth of white PLA failures, print failures, support material, strands of filament, etc., from Print City. Once you've got all that, are you sure that it's all the material that you want? So on the left is just a quick picture of all the things I pulled out of the bin that was supposed to be PLA only. A lot of the things on here, you can see some little kind of electrodes, stuff that we use in the lab. There's bits of caps and tape for the bed, there's tissues, lab gloves, all sorts of stuff. And on the right is the Print City waste. So we also have a lot of resin printers, SLS, MJF, that kind of technology. So there was lots of kind of resin support structures, bits of sweet wrappers from students, all sorts of stuff ended up in there. So you have to manually sort through all that. There's no real system to do that yet. Once you've done that, you end up with some theoretically clean waste. So on the left is multicolored PLA, on the right is just the white PLA separated. What do you do with it then? Most people use a shredder. On the left is a shredder. You're looking around £500. Sorry for anyone in different currencies. You can convert at your own leisure. £500-ish will get you a decent shredder. From that, you get these kind of chunks. A shredder rips things apart. You get lots of different shaped chunks of plastic, and you get lots of dust. A granulator is what you use in industry when you're recycling part from an injection molder, and it uses fixed knives and a set screen, so you can set the size of the plastic granules you get out. And that picture on the right, is the ground up white 3D prints and filament. And you see the much more uniform, much more usable size for 3D printing. But the downside is the granulators cost upwards of £5,000 and £10,000, all the way up to 60, 70 if you need to process a lot of plastics. Once you've done that though, you've got some multicolored PLA, some white PLA. But what you can notice about this is while the big chunks are uniform, there's lots of little tiny strands of filament, there's lots of dust. And that doesn't really play well with extruders. So we need to then take this 10 kilos of waste in both of these, sieve it manually. Sieves aren't that big, so this takes quite a while to sieve all the dust out, and then you end up with just the granules you need. But what do you do then? So there's two different examples of what we can do. This first example is kind of medium scale, I wouldn't say large scale. This is a large thin screw extruder. You'd usually use this to compound different materials in industry. But these start from about £100,000. Huge extruder, we feed all the granules into there. Extruder roughly 3mm, the diameter is not hugely important. Through the water bath into the pelletizer, which is just only with knives on it, chops it up into little pellets, then goes into a pellet dryer. We've dried it in a water, we've cooled the plastic in a water bath. We need to get rid of the water because water ruins your 3D prints. A pellet dryer is about £10,000 for a pellet dryer that can hold, 5 kilos plus of material. It's adding up. Alternatively, at home, this is the kind of setup I've got on the Print City stand. I'll be doing a demo at some point today or tomorrow. These are about £6,000, which comparatively very cheap, but for me at home, I wouldn't have £6,000 to spend on that. My printer doesn't cost anywhere near that. So we extrude roughly 3mm filament again. Then you can use an open source pelletizer. This one from Teaching Tech on YouTube. Look at about £30 to make one of these yourself, and then not including a drill to drive it. And then an oven. Most people have an oven at home for free, so you need that to dry your pellets once you've made them. What do you do then? So the ones on the left, these are the nice multicolored 3D print waste. We've got some kind of not quite black, a little bit browny pellets. And then from the industrial Print City waste prints, we've got some nice white peeling pellets. I apologize for Green by 3D. I had to crop his head out to fit him in this image. You could go straight to printing with your pellets. There are some DIY kind of enthusiast products like the Green by 3D one, around £350 for a pellet extruder that fits on your end or your board at home. On the kind of more prosumer level, you've got the Dies Design. They've got Pulsar, which is a huge one, the Pulsar Atom, which is about £5,000 just for the extruder, not including how you get the pellets to the extruder, which is also something you need to consider. And then on the top end of it, this is my current research project. So this is a Rapid Fusion P320 extruder. Just the extruder is £20,000. All of the control equipment that goes with it is another £10,000, not including the robot. I hate to think how much the robot cell costs. We fortunately working with Autodesk on that, so they fully bill. But this is currently working on recycling aviation waste and automotive waste into molds for later carbon fiber and glass fiber. That's exciting. But most people aren't going to do that. I think this is, especially at Rep Festival, I think this is a good thing for you guys to go home and think about. Like we could do with better pellet printers. It's much cheaper to buy pellets, and it's much easier to store pellets than it is to buy filament. I can buy 20 kilos of white PLA pellets straight from the manufacturer for £50. Lasts a long time that when you're printing. But the hardware and slicing technology is a little bit behind, a lot behind filament printing, especially when it comes to retractions and settings like that. It's really quite difficult to dial in a screw extruder rather than a filament extruder, because you can't pull back on a filament when you've got pellets. If you don't have a pellet extruder, you've got to make it into filament. This is the EX2 extrusion line, which again we've got on the stand. You put your pellets in, heat it up. Extrusion temperatures tend to be a little bit lower than you print them at, although this changes depending on how many times you recycle the material. The more you recycle that same PLA, the lower the temperatures will get. So until you get to the point where the PLA is just liquid and you can't use it anymore, which is a lot of our research is based around how many times we can circularize the whole process before it's completely useless. This plastic that I've got on the stand, I actually mixed in 20% of food packaging and PLA as well. So it's not 100% 3D prints, but it would be exactly the same otherwise. The setting, the pull speed, and to set the diameter of the filament is very, very manual on most of these extruders. You need to spend a lot of money to get an automatic one. So you need someone with a lot of patience and a lot of skill to sit there and tweak the speeds to make sure your diameter stays the same. And the spooler, you're not going to get a perfectly spooled, nice cement roll. There's going to be gaps in the filament. Hopefully no tangles, but you need to sit there and babysit it. And then you've got your filament. We all know what you do with the filament. You print it. On the left, these are the exact same G-code file, I should mention, on a Prusa XL with a 0.4mm nozzle. On the left is the multicolored 3D prints. You're not going to see the benches in real life. They're on the stand again, and it's a little bit hard to see on the screen, but there's bits of Acton tape sticking out of the prints at random points. And you'll find bits of plastic that aren't actually PLA. So the little chunks of blue plastic in there, not sure what the plastic was, it was in the waste bin. It made the filament snap all the time if you got a chunk, or it clogs the nozzle because it's not high enough temperature to melt it. It's a bit of a nightmare. Whereas on the right, the print's fine. It's not as good as, you know, a nice Royal Cruciman. The diameter isn't quite as consistent, but it prints fine. If you're using it for prototypes, perfect. There's a nice, I'm not going to go over the whole process because Dr. Deflow on YouTube did a really good job of it. So you guys can go on the QR code or find it. But if you want to buy it off the shelf, the cheapest kind of package to do all of this, grinding, shredding, extruding, granulating, re-extruding, about £16,000. That's the cheapest full system I can buy at retail. So this is kind of the call to action for the RepRap guys. We need to make this, you know, under £2,000 ideally to make it worth it. You know, I could go to the Amazon, eBay, buy a spool of, you know, Sunloom filament, £14, £15 for a kilogram. Is it worth me spending £16,000 on a recycling? You know, how many prints do I realistically do to justify that much money? So kind of up to you guys. There's lots of, I'm not going to force you with questions, but these are just things to think about. I have written a full article on this, so if you guys want to read the full article, it'll be there in the presentation, or find me on LinkedIn. But yeah, there's a few major problems, I think, and I think RepRap Festival is the perfect place to present those. That's everything for me. Anyone's got any questions? Feel free.
Do you just want to go back to
Yeah, absolutely.
the QR code up there?
Yeah, I'll take any questions, please.
So basically, in the UK, in this we spend a lot of money, but no way of recycling our filament.
So we've got ways of recycling the prints and filament, but not back into filament. So there are companies like Prusman have it in Europe currently, but Filamentive have it in the UK, where you can, if you buy over a certain amount of filament from them, you'll get a box to put your 3D print failures in. You send it back to them, and it won't get made back into filament, but that waste stream gets taken out of landfill, and then they'll use it to injection mold spools or kind of low quality, low value items, whereas that material would otherwise go to landfill. So the loop isn't closed currently, but it isn't entirely open also.
Yeah, that still basically means there's not a lot we can do with it.
Yeah, essentially. I'm trying to kind of illustrate the costs involved with a company trying to do this. It is quite frustrating that this technology isn't there yet. We use so much filament, we don't really think about what to do with it afterwards.
As a hobby, I'm disgusted with myself.
Yeah, it's kind of the dirty secret of 3D printing.
The amount of plastic waste.
Absolutely, I agree. There's a gentleman on the back.
You talked about the actual machine cost.
Yeah.
Have you got any maths on the energy costs of recovering it?
That is currently something I'm researching. The energy costs are always going to be higher than virgin because we're going to have to process the prints. You're going to grind them up, whereas virgin plastic's coming in as perfect pellet form already. So there's the cost of grinding it or granulating it. There's the cost of extruding it to make it back into pellets. So we can either take, as mentioned there, we can remove a step potentially by designing an extruder that works with granulates and the dust. Because currently the filament's unusable if you use just regrind. I think Dr. Deflow goes into that on his video when it comes to 3D prints as well. We need like pretty consistent diameter. Also, my 0.05 most manufacturers quote. You can't get that with regrinds. It's very, very difficult. But yeah, we will be looking into the energy costs.
I mean, I got a couple of questions, but well, first, with respect to recycling, would this not be something where the government step in, set up a recycling center?
I mean, what's the investments? But yeah, absolutely. I think that should be something to look at. It's something we look at kind of institutionally on a larger scale. Like we have recycling centers for aluminum and for other materials, but we don't really look at 3D printing as an industry. But I think we should.
Could be cost effective.
It could be cost effective, yeah.
Did you look at a company called 3Devo?
Yes, I did. We make bespoke materials in our lab, so our equipment has to be kind of tailored towards. We put things into filament, you know, platinum graphene, that stuff that people don't really test or think about in our kind of sphere of use. So 3D Evo would look like a brilliant product, but not really applicable for us to try. And the whole subscription model rather than selling items doesn't really fit into education or research for us.
But for the recycling, not so much.
Yeah, absolutely. For print recycling, so I've already forgotten the name of the company.
3D.
Green Evo. Yeah, I did have quite a lot of thoughts from the guys at TCT. And for recycling, as long as you've got a pure waste stream, yeah, the results were pretty good. The filament wasn't perfectly round, but the diameter was pretty consistent. But again, you can't just outright buy their equipment anymore. You have to really buy a subscription now. So a lot of people, that might be a plus for some people who've got to give it a try, but for a university, it's fairly applicable.
So what you've just highlighted there is quite a narrow use case. You've got a narrow selection of input for the bank and a narrow selection of needs. I'm assuming then that it's going to be virtually impossible to take more general plastics, possibly people's recycle bins, to actually be able to push into making pellets of filaments for either our use or even the other way around.
Absolutely.
Pushing our filaments into the general recycling.
Yeah, absolutely. The waste separation is the key issue here. There isn't currently a good way to do it. It's manual. Yeah, that's a call on the RepRap community again. If you could think of a way to, I mean, not only you'll make a lot of money out of doing it, but you'll make a very big impact. A lot of these, excuse me, a lot of these as well. You'll see, like up here, this is just kind of when we're using bespoke materials in the lab, we'll just do, a little Batman or something to purge what's left in the extruder rather than sitting there and keep saying no, the color isn't correct on the crucibles. We just do a print. So some of these will be, 99% pure, but 1% contaminant, and there's no real way to separate that out other than me looking at it and saying, no, that's not purging it, get rid of it. Potentially looking into kind of IR and spectroscopic cameras to see if there is a way to separate it automatically, but it's a really, really difficult problem that needs solving.